Okay, students, then we are starting today's class, day 19. Okay, and what we have today is capacitance. Right. So, what capacitance is? Capacitance is a device which is used to store energy. And how we store energy in this? By charging the two plates of capacitor. Okay, two plates of capacitor I am talking because primarily our focus is on parallel plate capacitor. Right. So, what is capacitor? A device that stores energy. Okay, that stores energy first. Now the question is how? By charging two plates of capacitor. By charging two plates of capacitor. Okay, so as I said that we are primarily focusing on parallel plate capacitor. So if we have two plates, parallel plates, now what we are doing? Both are neutral obviously. Okay, so when we are going to connect them with battery. Okay, when you connected them with the battery, what happens then? Potential difference is developed. So from here, electrons start moving in this direction. Okay, electron starts moving from here to here and goes to the positive plate of the battery, and then battery works over them. Okay, battery works over them and bring them over here, and then again they move to this plate. So same electrons are coming over here. This plate becomes negative and this plate becomes positive. So maybe the charge on this one becomes Q and charge on this one becomes minus Q. And when the potential difference across this is equal to potential difference across battery, then the flow of charge stops. Until this potential is same, electrons keeps on moving from this plate to this plate. And in doing so, energy is stored inside the capacitor. How much energy is stored? We will see it. Okay, but this is the process. So what we did is we charged these two plates equally. One is positively charged, other one is negatively charged, and in doing so, we stored energy. Where we use this energy? We can use it if suppose that this battery we remove. Okay, and if we connect one multimeter or ammeter, then we can see that current is there between them. Or if we connect one small bulb here, we connect a small bulb. Okay, this is here and we are connecting a small bulb here. Then what happens? Current will start flowing because your potential difference is there. And we can see the current. Okay, this bulb will glow and we can see the current effect of that. But after some time, that energy will be out. Okay, why? Because from here now what is happening in this case? Current is here like this, true. But what about the electrons? Electrons are here. Here are more electrons. Okay, so electron starts moving. This was having excess electrons. Now electron starts moving here like this. So in this one, it starts losing electrons and this starts gaining electrons. So because of that, what happens? Charge on this also decreases, charge on this also decreases. Because this was having a deficiency of electrons, you got the electrons. And this was having excess of electrons. This is losing electrons. Finally, what will happen? This will become chargeless, this will become chargeless. And potential difference across them will become zero. Then current will stop. This is discharging of capacitor, this is charging of capacitor. Okay. So capacitor is a device which is used to store energy, and this is how we utilize it. So can it work like a battery? Answer is no. Battery is a constant source of energy that supplies energy continuously. Okay, but this gives you an instant energy only. Okay, capacitor gives you instant energy and it discharges very fast. Whereas battery keeps giving us the energy for very, very long time. Because in this one, potential difference is maintained. Okay, we maintain this V, but here it's not like that. Okay. Alright, so parallel plate capacitor, we already have discussed that this is only in our syllabus. Okay, but still we discuss a little bit about spherical capacitor also. Parallel plate capacitor. Okay, so this is parallel plate capacitor and we connected this with a battery. Okay, charge on this is plus Q, charge on this is minus Q. This separation between the two plates is very, very small. It's very, very small as compared to the size of the plates. Always remember, okay? Separation between plates is very less as compared to size of plates, compared to size of plates. Okay, now what are we trying to do in this one? First of all, we didn't discuss that what is capacitance, right? So, capacitance, if I go back in this one, capacitance, what is capacitance? That we didn't discuss, right? So, potential here, if suppose this potential I am talking, if in place of this V, if I am going to put here 2V, then what will happen? Then here also potential has to be 2V, no? If here is 2V, because we know that till this potential is not between these two plates, charge will keep on flowing, okay, until this becomes 2V. So if this is 2V, then charge here, let me discuss in this way, okay. Suppose this is a parallel plate here, okay. First, we had potential difference V here. So here also potential difference came V, okay. And here charge came Q and here minus Q. Now we change it. Now we are having a battery of potential difference 2V. Now what will happen? Here potential difference also will be 2V. Then how much charge will be here? Now it will be 2Q and minus 2. Same way if I am going to have this as a 3V, then here charge will become 3Q. So can we say that the charge on the capacitor is directly proportional to the potential difference that we applied across it? Yes. Charge on capacitor is directly proportional to potential difference of the battery or potential difference applied. Okay, now remove the proportionality. Right? So we remove the proportionality and brought one constant which is C, and this C constant only we are calling as capacitance. Okay, the C only we are calling as capacitance. So what is capacitance actually? C is equal to Q by V applied, or you can say potential difference between the plates. Okay, Q is what? Charge on positive plate by potential difference between two plates. Right. So this is capacitance. Capacitance unit is farad. Okay. Unit of this is farad. Unit is farad. Okay. Dimensions also Q by V. So dimensions of Q is 80. Okay, ampere second. So dimensions also we'll see here itself. Okay, Q's dimension is 80, and below that is what? Potential. Potential is what? Potential energy per unit charge. That means joule per coulomb. So joule per coulomb. So joule per coulomb means is m L square T minus 2, that is joule, by coulomb, that is 80. So what we got? A square T square by m L square T minus 2. So finally dimensions are m to the power minus 1, L to the power minus 2, A square T to the power 4. M minus 1, L to the power minus 2, A square T to the power 4. That is the dimension of capacitance. Okay, right. So let's see then what we were doing over here. We were talking about the capacitance of parallel plate capacitor, how much it is. It depends on what. So we are saying that separation between the plates is very less as compared to the size of plates. Point number one. Second thing is, if we want to find out capacitance, we know that we require charge on positive plates by potential difference here. Directly we can write Q. No, we are not writing that. Okay, we have to find it, how much it is. So what happens here, if this has got charge Q and this charge got minus, rather, this plate got charge Q and this plate got charge minus Q, then electric field is there between positive charge and negative charge. We know that electric field will be like this. Okay, so what is this electric field, that we'll calculate first. Okay, so electric field for this will be sigma by 2 epsilon naught in this direction. Sigma by 2 epsilon naught. Whose field? This field. Sigma by 2 epsilon naught. Same way, this charge field also, this is minus Q. So minus Q's field will be towards it, like this. That is also sigma by 2 epsilon naught. Okay, so here total field is what? Sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So electric field is coming sigma by epsilon naught. And electric field is what? dV by dr. That means potential difference by separation. So we can say that potential difference here delta V and separation is d. So I can write this as delta V by d. So delta V is what? Delta V is sigma d by epsilon naught. And sigma is what? Q by A. This is delta V. And Q is what? Charge on positive plate. So let's put it over here. So we got C value. Q by QD epsilon naught A. The Q gets cancelled. C is epsilon naught A by. So capacitance of a capacitor doesn't depend on how much charge you have given. It depends on its size, A and D, and it may depend on its medium also. Okay, so capacitance of a capacitor depends on size and dimension of capacitor. Dimension of capacitor and medium between two plates. Medium between two plates. Okay, now suppose that we are going to have a medium whose dielectric constant is K in between. Okay, in that case what happens? Its capacitance will become K epsilon naught A by D, right? Because its medium will become having permittivity epsilon. Okay, so if suppose we make it, this is here a capacitor and we are fully filling it, right? So if we are going to fill it fully like this, okay, and we are saying that its dielectric constant is K or permittivity is epsilon. Okay, so in this case what will be C? C will be epsilon A by D, and epsilon we will write as what? K epsilon naught A by D. Okay, here I did a mistake. This is epsilon, right? So it becomes K epsilon naught A by D. So by inserting dielectric, are we increasing the capacitance? Answer is yes. When you putting this dielectric inside, the capacitance is increasing. Okay, right? Capacitance with dielectric. So we saw that when we are going to insert a dielectric, capacitance increases. On inserting dielectric, capacitance of capacitor increases. Okay, capacitance of capacitor increases. Alright, but if we insert in this way, something like this we have, and in between we are inserting something like this it is. Okay, so here we will say this separation between two plates is R. Okay, and this is T. Here dielectric constant is T. So here plus Q will come, here minus Q will come. Okay, now what we have to do for capacitance, we have to write C equal to Q by delta V. So we have to find how much is potential difference between these two plates. How to calculate? So suppose this plate is, I am giving A name and this is B here, this is C and this. So VA minus VD we have to find. And VA minus VD we are saying is actually equal to VA minus VB plus VB minus VC plus VC minus VD. Okay, so what happens here in this one? Here in this air medium is there. Okay, vacuum is there or air you can take. So here electric field is, let's say, E naught. Okay, when this goes inside a dielectric medium, then electric field decreases and becomes E naught by K. We have seen now this one in electrostatics when there is a force between two charges, it 1 by 4 pi epsilon naught K, Q1 Q2 by R square. Whereas in air it is 1 by 4 pi epsilon naught. So in a dielectric medium, force becomes 1 by K times. So electric field also becomes 1 by K times. Okay. This is again back to the same medium. So here again electric field is E naught. Now it's easy for us to write VA minus VB. Okay, now VA minus VB and VC minus VD in this one and in this one. Okay, actually the electric field is same. So if for the time being I assume this is X. So what I can do, VA minus VB we can write as E naught into R minus T minus X. dV equal to E dr, right? So E into D plus VC minus VD also we can write in the same way. What will write? E naught into X plus VB minus VC. What is that? E naught by K into T. That is all. Okay. So you can see that here what is happening? E naught into minus X plus E naught into X, that will get cancelled. So what we will be getting? E naught into R minus T plus E naught by K into T. This is VA minus VD. We'll keep it over here. C equal to Q by E naught you take common, R minus T plus T by K. And E naught is what? E naught is sigma by epsilon naught. Sigma is what? Q by A. Okay, so put it here. So Q by Q to A epsilon naught R minus T plus T by K. This is getting cancelled. So what we got? Epsilon naught A by R minus T plus T by K. This is the capacitance. Okay, you should remember this. It's important. Now, if suppose this is conducting medium. Conducting medium's K is infinite. Okay. For conducting medium or metal, for a conductor, K is infinite. So if this is a conducting medium, just K will be infinite. Our answer will be epsilon naught A by R minus T. Epsilon naught A by R minus T. Okay, if it is a conductor, then what is the problem? Potential difference is not here. Both these plates will have same potential difference. That's it. Because electric field used to be 0 in conductor. Here, inside a conductor, electric field is 0 because potential difference across two plates is not there. Okay, right. So it will become epsilon naught A R minus T if it is a conducting plate. Okay. Sometimes they ask you the question in this way also. What is that? Instead of showing you this, they will make They will make one capacitor like this, and in between one wire will be like this. Okay, in between one wire is there, and they may connect it with a battery. They'll ask you how much is the capacitance. How much is capacitance? There is no capacitance here. Okay, because C is equal to Q by delta V. But here no charge is stored. Where is the charge stored? Both are connected, no? How can you have positive Q and negative Q over here? Not possible. Both are connected. Okay. So it's complete circuit actually. This is a wire. It's working like a wire. Here is wire. It is going like this. It is very similar to if we are going to have a capacitor which is fully packed with a conductor. K equal to infinity. Both are same. So if K is infinity, then if we are talking about epsilon naught or K epsilon naught A by D, then okay. So capacitance seems to be infinite, but how much charge is stored? No charge is stored. Okay, no charge is stored. What is the potential difference? Zero. Okay, that's how much C equal to infinity. Okay, potential difference will be zero because both are neutral. No one is having any charge. Okay, so this and this are very much similar. Remember that. Okay. All right. Let's move ahead. Spherical capacitor. A spherical capacitor, to certain extent, we have seen in electrostatics also. The spherical capacitor. So when we charge this one, okay, when we are charging this, we are bringing the charge to this one. Here also potential increases. So if potential is going to increase, that means it can store energy. So C is what? The C is Q by delta V or Q by V here because this is a single capacitor. So no delta V. Or delta V also if you are writing, then you have to write this as infinity. Okay. Then we can say potential on this minus potential at infinity is delta V. Okay. So now charge you have given is Q and potential on this capacitor is what? Potential on this one will become 1 by 4 pi epsilon naught Q by R on its surface. Because when we give the charge to a conductor, we assume that the charge is coming where? At the center. So because at the center charge is available, the potential on its surface will be this. So let's put it 1 by 4 pi epsilon naught Q by R. Okay, so capacitance is 4 pi epsilon naught R. C equal to 4 pi epsilon naught R. Okay. So this also you can see that it depends on what is the size of the capacitor. So C here is directly proportional to R. Okay. Now there can be questions on this one. In electrostatics also we saw some questions on that one. Okay. So here also we can have the question on this one. The capacitance, the ratio of the capacitance to spherical capacitors R1 and R2, what will be the ratio of capacitance? If the charge density is sigma 1 and sigma 2, okay, then what will be the ratio of the capacitance? Something like that questions can be asked. Okay. Now we have combination of capacitors. Series and parallel combination. So let's see them. So series combination. Series combination. Series combination is this. Okay, C1, C2, and it's connected with a battery. Okay, now what happens in this one? When you are connecting it with the battery, here is potential difference V. So we know that here and here potential difference total should be V only. How? If I consider here is 0 volt, then here will be V volt. The same V volt will be here because potential is not dropping. No element is there. It's a conducting wire. Same way here will be 0. So if potential drops across this one is V1, that means how much is potential across these two plates? And here is V2. Then what we can say? V minus 0 equal to V1 plus V2. That means V equal to V1 plus V2. Correct? Okay. Now what about the charge? Now when you connected this with the battery, we know that from here electrons will come. Correct? Where it will go? To here. So this will become positive Q. This will become negative Q because of the battery. Then what will happen? From this plate, now this is negative Q, there is excess electrons. So this is going to repel electrons from here. It will repel electrons. So those electrons, now this is connected with a wire. Those electrons will flow here. So what will happen? This will become minus Q and this will become plus Q. So charges on this this capacitor also and this capacitor also is same. So same charge is there. So in series connection, we have same charge on capacitors. There is same charge on capacitors. Same charge on capacitors. Okay. Right. So same charge on capacitor means here what we can do? Here I can write this is Q by C1 and this is Q by C2. And this V we can write as Q by C. What are we trying to do? In place of these two capacitors, we are trying to have one capacitor which can take their place. So its capacitance is C. Okay, so what we are getting? 1 by C equal to 1 by C1 plus 1 by C2. 1 by C equal to 1 by C1 plus 1 by C2, or C equal to C1 C2 by C1 plus C2. The series connection. Okay, we know that. Then you have parallel connection. Okay, so we have parallel connection now. So this one, parallel connection when we do. Okay, so parallel connection you will see here. Parallel connection. Right. And parallel connection, what happens? We have same potential difference across capacitors. This is battery. Okay. So what will happen? This battery is going to take electrons from this plate also and from this plate also. Will it be same? Okay. Will it be same number of electrons? We can't say. Okay. We cannot say. But one thing we can say is, it will keep on taking the electrons from these plates till the potential difference here is not V and here also is not, because both are connected with the battery directly. So here also potential difference V, here also potential difference V. And if suppose here we can say this is C1 and here we say C2. Okay. So what we can say in this one? From here maybe some electrons, from here some electrons. So total electrons going in this one is whatever electrons have come from here plus whatever electrons have come from here. So we say in opposite way. We say that suppose that the total charge here is Q, here charge is Q2 and here charge is Q1. So we say here Q equal to Q1 plus Q2. What is Q1? C1V. Q2? C2V. So here CV equal to C1V plus C2V, that is C equal to C1 plus C2. This is parallel connection. Okay, so this is parallel connection for us. This is series connection, this is parallel connection. Okay, then multiple dielectric slabs. Okay, if we are going to have multiple dielectric slabs, then what type of questions can be asked from us? In fact, similar questions we did in thermal conductivity also. So same thing is here, okay, same thing, exactly same. Now suppose we have capacitor like this, okay. The separation between them is D and area of the plate. Area of the plate is A. Area of the plate means it's like this actually. This also. This is area of the plates. Okay. Now we have filled this with dielectric. So maybe we are filling it like this first. Okay. This is K1 here. This is K2. Right? K1 and K2. So then what will be the net capacitance? The question asks this. What we can say in this case, we'll say that this is one capacitor and this is another capacitor. Okay, this is one capacitor, this is another capacitor. Make it like this only, okay. So that it looks like what we are doing. Okay, so now this is one capacitor, this is another capacitor. How they are connected then? This is connected through a battery in this way. Okay, so from here you are taking some charge which is going in this one. Then that charge is given to this. Okay, so this is positive, this is negative. What about this? So this, because of this negative, it is going to repel electrons. They will come on this one. Correct or not? So this will become a negative plate and this side becomes a positive plate. So these two capacitors are like this. The series connection. The series connection. The C1 and this is C2. So net capacitance we know is C1 C2 by C1 plus C2. But what is C1? C1 actually is K1 epsilon naught A by D by 2. Yes. Now it depends, like they can give us D by 3, this will be 2D by 3, D by 4, 3D by 4. Depends. Okay. So K1 epsilon naught A D by 2 and C2 K2 epsilon naught A D by 2. Now we are going to put it over here. Okay. I think it will be better that if you do 1 by C equal to 1 by C1 plus 1 by C2. It will be easy. Okay. So 1 by C2 means 1 by C1 means what? D by 2 by this. So it will be better for us to write that D by 2 by K epsilon naught A, K1 epsilon naught A, here is D by 2, K2 epsilon naught A, and here 1 by C will be right what? D by K, that is effective epsilon naught A. Okay, so what we are going to get? Epsilon naught A we can cancel. So D by K equal to D by 2 K1 plus D by 2 K2. Okay, this D is also going to cancel. So what you will be getting? 1 by K equal to 1 by 2 you take here, 1 by K1 plus 1 by K2. Okay, like this we can find the value of K, but 2 K1 K2 by K1 plus K2. 2 K1 K2 by K1 plus K2 is coming. Okay, like this we can do. Then if we change it, we are going to make it parallel then. Okay, see then. Next question if we write, if it's parallel, it's like this. This is K1, this is K2. Okay, then what will be the net effective thermal, no, not thermal conductivity, effective conductivity. Okay. What we can do in this one? What we can say in this one? This is connected with a battery and we are saying them this is one capacitor and this is another capacitor. Okay, so from here also charge is being taken by this battery, from here also charge is being taken by this battery. It will be taken till the potential difference across this as well as this is same. That means a parallel connection. Okay, so in parallel connection what we have? C equal to C1 plus C2. So what you can do? K1 epsilon naught A by 2 by D. Here area has become half. Same way this one. K2 epsilon naught A by 2 by D. And here what you will write? K effective epsilon naught A by D. So what you will be getting? Epsilon naught A by D we can cancel. So K equal to K1 by 2 plus K2 by 2. Okay, K1 plus K2 by 2. If the same one, similar capacitor, we change like this. like this. Okay, so we say that here there is K1, this is K2, this is K. This also we can do. Okay, what will be the K value in this case? Now we can say that the upper one and the below, they are in parallel connection, but below one together they are in series. Okay, so if it's capacitance, I write C1, it's C2, it's C3. First you solve this one. Okay, so their capacitance is what? Let's say its capacitance we are writing as C dash, which will be what? C2 C3 by C2 plus C3. Okay, then C net will be what? Now this C dash, in place of this I am writing C dash. So this becomes like this. This is C1 here, this is C dash. Okay, C net is what? C net is C1 plus C dash. That means C1 plus C2 C3 by C2 plus C3. Okay, now let's put it. C1 is what? Say K1 epsilon naught A by 2D plus C2. Now C2 is what? C2 first you write here. C2 is actually K2 epsilon naught A by 2 by D by 2. Its area is also half and separation is also half. So this is cancelled. So what we are getting? K2 epsilon naught A by D. So K2 epsilon naught A by D. Same way C3, K3 epsilon naught A by D by epsilon naught A by D you take common. Then you have K2 plus K3. This we have to solve. This one epsilon naught A by D and this epsilon naught A by D cancelled. And here C net is what? K epsilon naught A by D. Okay, so we will solve this one and we'll get the answer. So this way we can find out if they are asking us what is effective K value. Effective capacitance, we already know if simple series and parallel are given, what is there, and we are using in that. Okay, exactly same thing you did in conduction of heat. Okay, there we were finding thermal conductivity. Here we are finding electrical conductivity. Okay. All right. Then multiple plate capacitors. Now we saw that multiple dielectric capacitors. Now this is a multiple plate capacitor. Okay. So in this one, what is there? This is a battery. Okay. This is positive is connected over here and negative is connected over here. So we can say this is positive plate and this is also positive plate, whereas this is negative plate. Okay. So what happens now? Now this becomes one capacitor. This capacitor 1 and this is capacitor 2. So if we make it in a circuit, how it will be? Say this is plate 1, this is plate 2, this is plate 3. Okay, so between plate 1 and plate 2 there is capacitor and plate 1 is connected with a battery. Okay, plate 1, plate 2. Then there is a capacitor between 2 and 3 also. So 2 and 3. And it's connected like this. Is it connected like this? No, I have connected it wrong. Why wrong? Because plate 1 and plate 3 both are connected with the positive end of the battery. So plate 3 is here. Plate 3. Now see, both are positive. Yes, and here is plate 2. No issues. It's like this. Now check. Is it okay or not? Plate 2 is connected with the negative end of the battery and 1 and 3 are connected with the positive. So this is C. This is also C. So C net is what? 2C. They are connected parallel. Two capacitors, they are connected parallel. So it's like this. Okay. Let's see one more. Okay. Here 4 plates are there. First one is connected with the positive end and fourth one is connected with the negative end. Okay. Fine. So plate 1, plate 2, plate 3, plate 4. So plate 1 is making a capacitor with plate 2. Plate 2 will be making with this one, and plate 3 is making with plate 4. So there is possibility of 3 capacitors here. Okay. How? It's very simple. No? When you are connecting this with a battery like this one, from here charge will go to this. Then whatever the charge is coming on this one, it will repel the electron of this one. So those electron will go to this one. So like this, it will charge. So there will become 3 capacitors here. Looks like series connection, no? Right? First plate connected with the positive. Then there is second plate. Okay. Then the second plate is connected with the third one. And then third plate is connected with the fourth one. And first plate and fourth plate are actually connected with the positive and negative end of the battery. Perfect. Right. Perfect this one. They are connected in series. Correct. So what it will be? 1 by C equal to 1 by C1 plus 1 by C2 plus 1 by C3. Sometimes they will give you area is A and separation is D. So okay, fine. C1 and C2 and C3 value we have. We'll put in this one. So here is what? 1 by C equal to 1 by C1 plus 1 by C2 plus 1 by C3. Okay. Right. Let's move ahead. Okay. This is there. Now this is positive and this is negative. So this is plate 1, plate 2, plate 3, plate 4. So between plate 1 and 2, 2 is connected with the negative end of the battery, first one is connected with the positive end. Okay, then 2 and 3 is also a capacitor. So 3 is connected with the positive end, 2 is connected with the negative end. Okay, 3 and 4, again this is positive, this is negative. That means all are directly connected with positive and negative end of the battery. That means across this also potential difference is V, across this also potential difference V, across this also potential difference V. Parallel connection. It will be what? C1 plus C2 plus C3. Right? So plate number 1, okay, with plate number 2, direct connection with battery. Okay, then plate number 2 and plate number 3. Plate number 3, plate number 2. Then plate number 3 and 4. Plate number 3, plate number 4. Connected like this, and there is a battery here. So it's a parallel connection. Simple. Like this, we can find out the capacitance of multiple plate capacitors. Okay. Right. Let's go for something else. Now there is a question. What question is asking us? Question is asking, there are two capacitors. We can see they are connected in series. Right. Find potential at home. Here is 20 volt, here is 8 volt. So potential difference is 12. You can say that there is a battery of 12 volt. Your wish. And you want to find out how much is potential. Okay. You want to find out how much is potential. So, how to do? One way is we calculate the net capacitance, make it as series connection net capacitance we can calculate. And then we can find how much is the net charge. Then how much is potential drop on this one. Shall I show you? Method 1. I don't know whether you like method 1. Method 2 is better, but still the first thing that we think whenever this connections are there, we think it like this only. Okay, so these are two series connections. So what is C? C1, C2 by C1 plus C2. That is 8 into 4 by 8 plus 4. That is 32 by 12. Net capacitance. What is the potential difference across this? 12. So charge will be Q equal to C delta V. 32 by 12 into 12. The charge is 32 coulomb. Correct. So 32 coulomb is coming from here. How much is going to drop across this one? Okay, potential 1, P1, V1 is 32 by 4. That is 8 volt will drop. 8 volt will drop across this. So here what is the potential? 20 volt. Here 8 volt drops. So how much here is 12 volt? Method number 1. Method number 2. Method number 2 is based on Kirchhoff's junction law. Okay, Kirchhoff's junction law, KJL. What you'll do? I'm going to assume here potential is V. And if Kirchhoff's junction law is what? The sum of all the currents at any junction is equal to 0, or sum of incoming current is equal to sum of outgoing current. Okay. What we are going to do here? Sum of all currents is 0 in this one. Okay. Or sum of all the charges is 0. So what we will do in that case? This we are going to consider on the higher side. So here some charge will go, let's say there is Q2, and here some charge will go, that is Q1. Q1 plus Q2 equal to 0 I am going to do. Okay. What is Q1? You will say V minus 20 delta V into C. Q is that only to C delta V. So V minus 20 into C. How much is that? 4 plus. Here also same. V minus 8 into 8. V minus 8 into 8 equal to 0. So what we have? 4V minus 80 plus 8V minus 64 equal to 0. 8 plus 4 is 12 and 80 plus 64 is 144. 144. So V equal to 12. Both methods are there in front of you. KJL is also there, and the normal method that we opt, that is also there in front of you. It's your wish. Okay, which one you want to use it? It's your wish. Whichever you find easy, we can use it. Okay, next. Next is again similar one. There is a junction here, and we have to find VO. Same way junction law will apply. That is easy. Okay, so a junction law, when we are applying, what we are saying? Q1 plus Q2 plus Q3 equal to 0. Okay. Q1 means VO minus 20, or V, we will say V. V minus 20 into 2 plus V minus 2 into 6 plus V minus 10 into 3 equal to 0. So what we got? 2V minus 40 plus 6V minus 12 plus 3V minus 30 equal to 0. Okay, so 2V plus 6V, 8, 8 plus 3, 11V, minus 40, minus 12, minus 52, minus 52, and this is minus 82. So V equal to 82 by 11. That's the answer. Okay, so this way we can find easily what is the potential at any junction. Okay, right? Effect of dielectric on insertion in capacitor. So we already know that if you are having a dielectric, the capacitance increases, it becomes K times. If dielectric constant is K, then it becomes K times. And if it is a conductor, then it becomes infinite, right? Correct. Infinite means is whatever charge you are trying to give to one plate. Okay. Actually, what is the capacity? Like when we can say that the capacitance is this much only it can store. It will not be able to store more than that. Actually, what happens is there is something called dielectric strength. Okay. Dielectric strength. Or we discuss about permittivity. Okay, permittivity was what? It was opposition to the electric field. How much it can oppose? There is a limit it can oppose, right? After that limit, what happens? It becomes a conductor. It cannot oppose. After that, it becomes a conductor. So that means you cannot store the charge on the capacitor plates, because charge will start flowing from one plate to another plate. Normally, what happens when we talk about a capacitor here? The charge is flowing from one plate to the other plate because of this battery. Battery is making it. So this becoming positive Q and this becoming minus Q. And there is potential difference across it. Reverse flow is not possible. Correct. But if we are having a conducting plate or you are connecting them with the wire, then what will happen? Direct flow is possible. So when direct flow is possible, can you still keep them charged? Answer is no. They'll become neutral. They'll run away. Okay. So this is what happens when we talk about if you are having a conductor in between. So we say that there is capacitance is infinite. That means no matter how much battery you are applying, okay, there will be flow of charge happening. From here flow of charge will happen, true, but here also flow of charge is happening. Okay, it's very similar to if suppose that we have a water tank with base is not there. So how much water you can give to this one? Infinite, because it's not storing at all. Is it storing? Because base is not there. The same way here also, is it storing? No, because it's connected. So keep on giving it, doesn't make any difference. So we say that its capacitance is infinity. But how much is energy? It cannot give any energy to us. Okay. So it all depends on dielectric strength actually. If the dielectric strength means is the limit to which it can oppose the electric field. Once that limit is reached, after that your the dielectric becomes a conductor. And once it becomes a conductor, then storage is not going to happen. So that's called dielectric strength. Okay. All right then. Then this one, what we have is effect of dielectric in insertion in capacitor. So what we are doing here, suppose we have a battery connected with the capacitor and you are inserting a dielectric. Okay, we are inserting a dielectric here. And dielectric constant is K. Okay. What happens? Now if it is connected with the battery, so battery will make sure that the potential difference across them is V. Okay, if it is something else, then still battery will work. It will make the charge to flow so that the potential difference becomes V only. Then only it will stop. That is the work of the battery. If the potential difference is not here V, then charge will keep on flowing. So potential difference here will be V on. What happens to capacitance? Capacitance has become K times. We know that. Whenever you insert a dielectric in the capacitor, capacitance becomes K times. Potential difference is V only. Okay. All right. What about electric field? Electric field will be same. Net electric field will be same only. Then only the potential difference is same now. Okay. What about energy? Okay. We haven't talked about energy so far. So let's assume we know the energy already. Okay. So energy normally is what? Half CV square. So here energy will become what? Energy will become half Kc V square, because capacitance has become Kc. So here energy is increased. Energy has increased because it is able to store more charge in this one. How much is charge? Earlier Q was Cv, but Q dash is Kc. Because you are putting dielectric, it can store more charge as compared to before. Reason? Because it's difficult for these charges, okay, to move from here to here. Earlier there was only air. Okay, so if you are going to apply certain potential difference over here, you can change air into a conducting medium. Okay, but if suppose there you are putting a dielectric, okay, so then you require even more potential to make it as conductor. So that means you can give more charge to this. More potential difference you can apply over this. Okay, because you have put a dielectric. So what you are doing, you are increasing its capacity. You are increasing capacity means you are increasing its charge holding capacity. When you are increasing charge holding capacity means you are increasing energy stored in that as well. Okay, so effect of dielectric in the capacitor while it's connected with a battery. And if suppose that it's not connected with a battery, then okay. So if it is like this, if we already have charged capacitor, okay, we have charged capacitor, and then in this one we are inserting the dielectric. Then what happens? Okay, this is dielectric. In a charge capacitor we are inserting. So in this one charge remains constant. In this one what was constant? V. Okay, here charge is constant. But capacitance has increased. Whenever you are going to insert a dielectric, capacitance is going to increase, whether it's connected with the battery or it's not connected with the battery. Capacitance will increase. Okay. Then what about V? Potential. Earlier potential was Q by C, but now V dash is Q is same Q, but capacitance has increased. No? So potential has gone down. It has become V by K. Then energy. Earlier energy was half CV square, or in this case I will say Q square by 2C. Now energy Q square, Q is same only, but here this is Kc. So energy has decreased, it become 1 by K times. Here energy was increased, it becomes 1 by K, not 1 by K, it become K times. Here energy was K times, here energy became 1 by K times. Difference between the two. Okay, so remember that. Then energy stored. Energy stored should have been before that one, right? So energy stored is what? So what happens actually when there is a battery connected with a capacitor and you are charging it? Okay, this is V. So we all know that this is going to lose the electrons. This is going to gain the electrons. This is going to be positive charge. This is going to be negative charge. And finally, if suppose its capacitance is C, and finally potential across this will be V. The charge on this one will be plus CV, charge on this will be minus C. Right? And okay, fine. So what is the energy in this one? What is the energy stored in this one? So question is the charge directly CV came over here or slowly it became like this? At one instant or it takes time? It takes time, takes little time. So that means charge was slowly coming on this one. So what we can say? So energy stored actually is work done, right? Work done in storing charge or work done in charging. Okay, so what we did, initially suppose dq charge was given to it. Initially dq charge is here. So if dq charge is there, capacitance is constant only, no? Capacitance is C. Okay, its capacitance is C. So how much is initial potential on that one? Say dq by C. Then you are bringing q charge. Okay. So work done is what? Q delta V, we know that. Okay. So Q into V. What is V? dq by C. Now we are integrating it. From 0 to Q, let's say total charge is Q we want. What's going to come? Okay, 1 by C. Q dq means Q square by 2. This is 0 to Q. So we got Q square by 2C. This is the energy. Or work done in charging. Q square by 2C. Okay. This can be written in another forms, that is half CV square. Or we can write it as half QV also. So this is the energy stored in capacitor. But now question is asked, how much is work done by battery? Work done by battery. So work done by battery again is Q delta V only. There is no change. But the question now is how much charge has passed through this one? CV is positive charge. That means electrons, total electrons of the magnitude CV has passed through this. Then only this charge is there. So from here equal to this one must have passed through this. So when the electrons are passing through this, the charge is passing through the battery. Battery is doing work then. Okay, so how much charge has passed? CV. And what is the potential difference? V. So work done by battery is CV square. Work done by battery is CV square. And how much is energy loss in the process? Energy loss is work done by battery minus energy stored in capacitor, or change in energy stored in capacitor, delta U in capacitor. U final minus U initial. Here what was U initial? 0. Okay, so CV square minus half CV square minus 0, that is half CV square. Okay, so how much energy is stored? Half CV square. Work done by battery, CV square. Heat loss or energy loss, work done by battery minus change in energy in capacitor. Okay, this is energy stored in capacitor. Let's see a few questions. Okay, so two capacitors are here. Charge is Q, capacitance C, charge is 3Q, capacitance is 2C, and we have to find ratio of energy. Fine, easy question. U1 by U2. So what is its energy? It's a Q square by 2C. What is its energy? Q square by 2C. Its energy 3Q square by 2C. So here is Q square by 2C into 4C by 9Q square. It's cancelled and this is 2. So answer is 2 by 9. Simple question. That one, find energy lost on connecting both. Okay, two capacitors are there. Capacitance C, potential V, and this one is capacitance 2C and it's uncharged. V is 0. You want to connect it. What's going to happen? We are connecting it. This is going to charge it. Very simple. It will charge it till potential on both becomes same. Final potential will be same. Okay. So what it is based on? It's a conservation of charge. It's based on conservation of charge. The charge is not going anywhere. Okay. So what is initial charge? Qi. Qi is only with this one because here potential is 0. So Qi is CV. Okay. Finally, what will happen? There will be charge on this one also and charge on this one also. So Qi equal to Q1 plus Q2. Okay, and we said that both will have same potential also, because till the potential becomes same, charge will keep on flowing. So let's say final potential is V naught. So Q1 will become CV naught here and Q2 will become 2 CV naught equal to Q. Q is what? CV. So this is 3 CV naught. CV equal to 3 CV naught. C cancelled. V naught is equal to V by 3. Okay, what is question asking? Find energy lost. So first we got what is the common potential. Now we'll talk about energy loss. So what is initial energy? Say Ui. Ui is half CV square. What is final energy? Now these two are having same potential. Okay, so U final is half C into V naught by, sorry, not V naught, V by 3. V naught is V by 3. Okay, half C V by 3 whole square plus half 2C V by 3 whole square. Find the difference. Okay. If we want to remember the formula, there is one formula also through which we can directly find the answer. Okay. Even this was also not required to find common potential. If direct formula we remember. What is that formula? Energy loss formula is, or first we'll make one line, segregate that. Okay. Hey, remove this. Okay. So energy loss. What is the formula? 1 by 2 C1 C2 by C1 plus C2 into V1 minus V2 whole square. So whatever we are going to get from there, same we'll get from here. You can check it. So this is half CV square. How much is this? This is actually 1 by 2 into 3C, C plus 2C into V square by 9. Okay, this is like this. So we are getting here, this is CV square by 2, this is CV square by 6. So loss will be CV square by 2 minus CV square by 6. I think CV square by 3 will be the loss. Yes, loss is CV square by 3. Okay, check here. Are we getting the same answer? Okay, so 1 by 2 C into 2C by C plus 2C means 3C, and here is V1 is V only and V2 is 0. Okay, 2 and 2 gets cancelled, C and C gets cancelled, the CV square by 3. Same. So if you remember this formula also, that's well and good. Okay, directly we can calculate energy loss when you are connecting two capacitors. Okay. Work done by battery in charging, we already have seen. Okay, work done by charge in battery is Q delta V. If CV is the charge which is flowing and potential difference across battery is V, then work done by battery is CV square. Okay, so work done by battery in charging is this. Okay, so I think this is it. Yes, this is it as far as capacitance is concerned. Capacitance is over. Now then, current electricity. Let's discuss few points we can discuss about current electricity also. In current electricity, the first thing that we have is types of material. Okay, types of material means conductor. We know a lot about conductor. Then we have semiconductor. And then we have insulator. Okay, conductor means what? We know that free electrons are there. Those free electrons are on the surface. They keeps moving on the surface. They are free. Okay, so because of that, when we apply any potential difference across them, those will start moving in a particular direction and we are going to get current because of that, because of the availability of free electrons. Insulator doesn't have free electrons. So even if you apply the potential difference across insulator, no current is there because there are no electrons to carry. Semiconductor is in between. Semiconductor has very few number of electrons. Okay, so do conduct but very less current, right? But then there is one thing that is asked from us, that is, what is the relation with the temperature? If we increase the temperature, then what happens? So if temperature is increased, what happens to conductor? We say its resistance increases, conductivity decreases. If temperature is increased, its resistance increases. Reason is, if you are increasing the temperature, the speed of electrons increases. Which speed? Random motion speed. If suppose that conductor is there at a normal room temperature, its electrons, and you are not applying it across any battery, no potential difference is applied. Are these electrons at rest? Answer is no. They are moving. They have very high speed because of the temperature. Okay, so when you apply the potential difference, then will they stop the earlier motion and they will start moving in the direction of potential difference? Answer is no. They will continue to move in that one, but because of the potential difference, you are still able to give them a force in a particular direction. So they will start moving in this direction also, and they are having their own motion before also. Okay, so when it will be better, if they are already having motion slower, then we can push them in this direction, then they can have a better motion in the direction of applied force. What I am saying is something like this. If suppose this is one conductor, okay, on this electrons are there, they are moving randomly, they are on the surface, okay, they are moving in all the directions, and net displacement is 0. Okay, they are coming back like this randomly, zigzag motion they are moving, okay, zigzag, something like this they will be going, then they will be coming, they like this they are moving. But when you apply the potential difference, there is a net displacement of all the electrons in this direction, or rather it should be in opposite direction. Okay, so electrons displacement is there in this direction, but it's very slow because they are already having their own velocity. If we increase the temperature even more, then their random velocity will increase even more. So it will be even more difficult for us to bring them to this direction, right? So we say that because temperature is increased, resistance also increases, because we are going to get less motion of electrons. Okay, so increase in temperature increases resistance. But in semiconductor, opposite thing happens. If you increase the temperature, here resistance decreases. Why? Because when you are increasing the temperature in semiconductors, you are making certain electrons to go on the surface. Already there are very less electrons on the surface. So you made some electrons free. So they reached on the surface. So now there are more electrons for conduction. Okay, so because of that, we say resistance decreases. Insulator also same. When temperature increases, resistance decreases. Okay, so we should know that how temperature plays, what is the role of temperature in resistance. Okay, right? Let's move ahead. Current. What is current? Flow of charge per unit time. Flow of charge per unit time. Okay, two types of current we can have. I average, we can say total charge flown in total time. Okay, or you can have I instantaneous flow of charge at a particular instant. You can write as dq by dt. Here is what? Q by t. This is dq by dt. Okay, fine. Right. There is a question. This is given instantaneous. If q is a function of time, means instantaneous value is given because q is changing with t. What is he asking? Find I at t equal to 2 seconds. So what to do? This is also asked me. This is also instantaneous. That means dq by dt we have to find. Very simple question. What you will do? This is 4t plus 5. Keep t equal to 2. That is 4 into 2 plus 5. That is 13 ampere. Okay, we all know that what is the unit of current? Ampere. Right? It's a fundamental unit. So we have discussed it already. 4 into 2 plus 5, 13 ampere here. Then another question says q equal to 2t square plus 3 coulomb. Find flow of charge from t equal to 2 to t equal to 5 seconds. How much charge is flown from t equal to 2 to t equal to 5 seconds? What shall I do? Find it. What is the charge value at t equal to 2 seconds? 2 into 2 square plus 3, that is 11. Then find q at t equal to 5. Then we will know that how much charge is flown. 2 into 5 square plus 3. This is 50. 50 plus 3, 53. And you know how much charge is flown? 53 minus 11. In how much time? Oh, the first is flow of charge. 53 minus 11. Okay. Flow of charge 53 minus 11 is 42. Then question is asked, find I average. So this is the total flown charge and how much time? 3 seconds. So I average is 42 by 3, that is 14 ampere. Okay, but if suppose that from here in integration we have to find it. Sometimes we are interested in that, right? Then what to do? How I average will be finding? I average will be I as a function of time, I instantaneous into dt by dt. This we have to use for I average. This I average. First I instantaneous you have to find, but in this one we didn't find. Without that itself we have found I average. I instantaneous means you have to differentiate that. Then you have to integrate that and then dt. So first differentiate, then integrate means this only will come. The 2t square plus 3. Okay. Then limits. What is the limit? 2 to 5 by 3 seconds here. So that's what we did. Okay. So it's not necessary always that we have to go with the integration, that you remember. Okay. But we should remember this. If suppose that instead of q, if I was given here, I was given, how much is I actually? If suppose we have to calculate I, which is dq by dt, that would have been 4t. Then we would have done like this. Okay, otherwise how we have done is in front of you. Okay, remember. Oh, why did this? This only. Yeah. All right. Relation between I1, I2 and T1 and T2. Now see this, what it is. Suppose this we'll say is I1 and I2 is asking. So V is this and R is this. So it's based on Ohm's law. Okay. Ohm's law is what? Ohm's law is, if there is a conductor, okay, if there is a conductor here, this is conductor. This conductor we are connecting with a battery. And this conductor's resistance is R. Then current can flow through this resistance only when you apply potential difference. Okay. So if here is V and here is 0, which we are calling as delta V, which is equal to V. Okay. So it says that current in that one is directly proportional to delta V. Okay. Current in this one will be directly proportional to how much potential difference we have applied. And we remove this proportionality. So we write delta V equal to IR. So I equal to delta V by R. This is what Ohm's law is. Correct. Now, by using Ohm's law, we have to find in this one, this is V and this is R. First relation you have to find between I1 and I2. I1 is greater, I2 is greater. So you see that if I1 I have to find, and this is graph between V and R, then actually this is slope. Okay. This is slope of VR graph. I is slope of VR graph. Now whose slope is more? Say this is theta 1. This is theta 2. Clearly theta 2 is greater than theta 1. Or tan theta 2 is greater than tan theta 1. Tan means is slope. And slope is what? This. So if this is the same wire, if it's the same wire, okay, then what I can say? What we will say that this is slope. Slope means is I. Okay, if it's the same wire, then tan theta 2 is more. That means I2 is greater than I1. Because I is only the slope of VR graph. So whose slope is more? Theta, tan theta 2. Tan theta 2 is more means I2 is greater than I1. Second question they are asking is, get the relation between T1 and T2, temperatures. Now what we can say? What are we going to say in this one? Now we say that I2 is greater than I1. I2 is greater than I1. So if temperature actually is going to increase, that means resistance is going to increase. If resistance is going to increase, that means current will be smaller. Okay, current is inversely proportional to temperature, we will say. Okay, current is inversely proportional to temperature. So if we are saying I1 by I2, then here it will become T2 by T1. Okay, so here is what? Here we are saying I2 by I1 is greater than 1. This is I2 by I1 is greater than 1. That means T1 by T2 is greater than 1. That means T1 is greater than T2. Okay, so these kinds of relations can be asked from you. Okay, based on Ohm's law. Find charge flow. Okay. This kind of questions also are possible. So let's put the values in this one here. Let's say this is 5 ampere, 2 seconds, this is 3 seconds, and this is 5 seconds. And here right, and here this is what? This is, let's say, minus 4 ampere. The total charge flown is how much? Now, I and T graph this is. How to get charge from here? Now, I know that I is actually dq by dt. So, dq equal to what? I dt. So, whenever this is there, integration, that means we are talking about area under IT curve. Okay, so let's find this area, this is positive area, this is negative area. So, negative area charge is scalar quantity. No, shall we add or subtract? Answer is we'll subtract. Because here current is negative. Current is negative means it's flowing in opposite direction. Okay, so if positive charge has flown like this for some time, then it has gone like this. Net charge flown we have to find. Okay, how much is the transfer of the charge? So in that one, we have to take this as negative one. We can't take it as positive. Okay. Okay, then how much is this? Now this is 5, this is 2. So this is triangle. So here will come 5 only. Okay. Half base into height. This is 5. This one. This is 1. So this will come 5 by 2. Okay. Then this one. This is 4. And this is 2. So this will come 4 only. So how much is the total charge flown? Charge flown from one side to the other side in 5 seconds. 5 minus 4, that is 1. 1 plus 5 by 2. Okay. 5 plus 5 by 2 minus 4. That is 1 plus 5 by 2. That is 7 by 2. Okay. So like this, we can solve the questions on graph. Okay. So that's it for today. We are finishing the class here. Okay. Scan it. Scan the QR code. Tomorrow's class, we will finish current electricity. Okay. So here is QR code, scan it.